Today we will start a new topic which is called Fourier series. Then the next thing will be Fourier analysis. Then we will, if we have time, we might go to the body plots. So the timeline for the expected for this week. Today is Monday, which we will again go start with chapter 5, which is Fourier series. Then on Wednesday, 27th, the reading is page 197, 201. Friday, 29th, the readings are page 201 until 212. Next week, April 1st, so the reading is page 216 until 218. Then April the 3rd, which is Wednesday, it will be exam 2 return and answers. So basically, we will go through the exam answers, and the exam will be returned to you in that lecture. You expect to see the grades posted on Canvas maybe by Tuesday, April 2nd. That's the timeline. Okay? And most likely the TA will take care of grading the exam, and also will take care of Wednesday lecture in 4/3. That lecture will not be recorded. I will not be here, the TA will take care of it. Okay? Then there will be an announcement about the grades. So again, they will be posted on Canvas. Then there will be an office hours for the TA. So if you need to see the TA to review the grades. So keep in mind the TA for the grading different than the TA in the lab. Okay. Then in 4/5, Friday, the readings are page 216, 218, and this is the due date for homework for 12. So this is the timeline for this week and next week. Okay, so again, expect to see the grades posted next week by Tuesday. Then on Wednesday, the exam will be returned. Okay. Now, before going to Fourier series, just a quick reminder about periodic signals. What do I mean by periodic signal? How can I know this signal is periodic? Yes?
It repeats.
Repetitive, yes. And there's must not only repetitive, it should be repetitive regularly. So what does this mean? Repeat itself every specific period of time. Every period of time. So basically, repeat itself every specific period of time. Okay? So, as an example, the sine wave. So the sine, we know it is bound between 1 and -1 and repeated itself forever, right? And if we put a magnitude, for example, a scale, it can, for example, bound between A and -A, and we see that it will be every specific period of time, it will be repeated. That period of time must be constant. It is a must. So we say that from here to here is T, here to here is T, here to here is T. Such that T is called period. That's why it's called periodic, because repeat itself every period, which is T. And we also make a definition, it's called frequency, which is how many times it will be repeated per second. So the period is seconds. So the frequency is actually 1 over the period, which is, in other words, it will be hertz. This is or 1 over second, or second inverse, or in other words hertz. Then also we define omega as angular frequency. As omega equal to pi times f, right? And the unit of it is radian per second. Then we can say x of t equals to a sine omega t. This is periodic signal. It's sinusoidal periodic, repeat itself every specific period of time. Or in other words, it can be a sine 2 pi times ft. And we already discussed about periodic earlier in this course, but here just like a quick reminder. Okay, so we know omega, we know what's omega, you know from circuit, you know from signals, 2 pi times f. You know what does S, A, which is the amplitude. And we know that the frequency is 1 over t hertz, etc. And the same thing for other part of signals. So whenever we say, for example, triangular, it's also periodic, because it repeats itself every specific period of time. And also when I say about the sawtooth signal, it's also periodic. Those are periodic. And they have their own frequency, they have their own period, but keep in mind this might not be the same as what we see in the sinusoidal. Okay? So we know this. Here is just like a quick reminder about the periodic signal. Now, Fourier series. What does Fourier series mean? What's the point of using Fourier series? Fourier series, the definition of it, which is any continuous periodic function. We know what does continuous mean. We know what does periodic function mean, right? Any continuous periodic function can be represented by an infinite sequence of sine and cosine functions. So for any signal that's, we know it's periodic, like as mentioned, sawtooth, triangular, square wave, pulse train, whatever, those, all of them, we can present them as sine and cosine, as a sum of sine and cosine. So basically, I would say that here is the overall general formula for any periodic signal. X of t equals a0 plus the sum from k equals to 1 up to infinity a sub k cosine k omega t plus b k sine k omega t. So we see that it's the sum, sine and cosine. So we have the first thing, a constant. This is called average value of x of t, or in other words, DC value of x of t. Then keep in mind k from 1 to infinity. So it is infinite series. This series will continue forever. K equal 1, 2, 3, 4. So we have different values of k. Equal 1, 2, 3, 4, until infinity. Okay? While t can be any number. T can be anything between negative infinity to infinity. But here k must be positive integer. It's k because it's a series. Okay? Yes?
What's inside the cosine and sine?
Cosine omega.
Is that k omega t?
Yeah, k omega. K omega naught t. And it's written omega naught. Omega naught is actually the frequency, is the angular frequency. So omega naught equals 2 pi times F naught. F naught is actually 1 over T. So here, omega naught is called fundamental angular frequency, while F naught is the frequency, so fundamental frequency. Fundamental frequency, while T is the period. Again, it's periodic. Then we know how to find 1 over F, 2 pi times F, and we know how to find it. Then the same beside the cosine, which is K omega naught T. So again, we put knots in purpose, not omega or not F, just to let you know this is the fundamental frequency, or related to the period, because it's periodic signals. So in other words, any signal can be presented into periodic signal, into sine or cosine, even if it's square wave, even if it's a hot string. But keep in mind, it must be infinite. It will last forever. From 1, 2, 3, until infinity. That's the mathematical representation. Then later we will try to see the practical parts, because most likely we cannot represent this until infinity in real life. What should I do? We will talk about this. Now, about the derivation, how we can find, what do I mean by A? So now we discussed, we know cosine, we know K, we know omega, we know T. K, omega, T. So the thing which is, how can I know a BK, how can I know AK, how can I know A0? Those are the formulas. So A0 equals 1 over T, the angle from 0 to T, x of T dt. Or in other words, it's the average value of x of T. A sub K, it will be 2 over T, the integral from 0 to T, x of T cosine K omega naught T dt, while BK, similar to AK, but it will be sine. 2 over T, the integral from 0 to T, x of T sine K omega naught T dt. So even though those are constants, but we need to calculate these constants. So yes, I can convert any signals into the formula which is sine or cosine, but there are some constants, we call it Fourier series coefficients. These coefficients are important. So A naught, AK, BK, those are Fourier series coefficients. Okay? Because now again, we can represent the sine, cosine, we know how the period, then we can put the general formula. But the thing or the challenge is in how to calculate the coefficients rooted in the integrals. That's just the challenges for you. Other than that, we know how to make the expansion of the series, we know how to find omega, we know how to find frequency, and that's it. So here, like some tables about telling you that the phasor domain is actually a special case, comes from Fourier analysis. We will go through this later, but just keep in mind that this Fourier analysis is a special case of Laplace transformation. Then, from Fourier analysis, we can derive the phasor domain that we know before that we did the AC circuits. Anyway, here is some trigonometric identity or some integrals, trigonometric integrals properties. So this one, we can use this especially when we do some integration, when we evaluate some integrals. So this table will be provided to you, so you don't need to memorize any of this or write this in the sheet. It will be provided to you because again, when we calculate the coefficients, we need to do some integrals. So there will be again some challenges, which is in evaluating the integral. But now, let's see, which is how to make the derivation, how we say A all equal the average value, how we say AK equal to this, BK equal to this, how we can calculate it, how we derive it. The derivation is for information, which is the derivation of the coefficients. Derivation of Fourier series as a shortcut, I'm going to write it as Fs, Fourier series coefficients. Let's start with A naught. Or before starting, I'm going to write over all function. We have x of t equals A naught plus the integral of the sum k equal 1 up to infinity. A sub k cosine k omega naught t plus bk sine k omega naught t. Then we need to calculate number 1, which is A naught, which is the average value. So, which is, in other words, 1 over t, the integral from 0 to t, x of t dt. In other words, substitute x of t with this long expression, then it's going to be 1 over t, the average value from 0 to t of a dt, a naught, plus from 0 to t, let's put inside the sum, let's put the sum first here, k equal 1, so infinity a sub k, or actually, from 0 to t, a sub k, cosine k omega naught t dt, plus the integral from 0 to t, the sum b sub k from k equal to 1 to infinity, sine k omega naught t. Okay? So I just try to split the integral into each term. Okay? Now, let's find the average value. What's the average value of the cosine? 0. What's the average value of the sine? 0. What's your next? This. So, A naught, or in other words, the average, equals 1 over t, then A naught times t, A naught, I'm sorry, here, times t minus 0, right? There's going to be 1 over t, A naught times t and t will cancel each other. This yields average equal to 0. Okay? I'm sorry, average equal to A naught. What we know about the average? Again, it's 1 over t, the integral from 0 to t, x of t dt equal A naught. This is the formula that we know. Right? Does this make sense? Now, let's go to the next one, which is how to calculate A. A sub k. What we need to do is, I'm going to make the integral from 0 to t, x of t, cosine, and omega naught t dt. Then, I will distribute the integral, substitute x of t with the long expression, and distribute the integral. So, it will be, with the first term, from 0 to t, A naught, cosine, and omega naught t, times dt, plus the other terms, which is the integral from 0 to t, the sum from k equal 1 to infinity, cosine k omega naught t, then cosine and omega naught t dt, then plus the third term, which is from 0 to t, the integral k equal 1 to infinity. Here I missed the k. Here's b, k. B sub k, cosine k omega naught, it's sine omega k omega naught t, plus or times cosine and omega naught t. Okay? Now we have the complexity of edges in evaluating the integrals. The integral of the cosine alone itself over a period of time, 0, right? Now the other thing, which is how can I calculate this term and this term? Especially, we have some challenges. We have k and k And we have here k can be changed. It's infinite series. So in other words, we can look at it as here. Sometimes we have each term. I can call this as term 1. Here's term 2. Each term 1 and 2 has two scenarios. What are these two scenarios? The first scenario, when k equal n, scenario A. Scenario B, when k does not equal to n. When k equal to n, in term A, cosine and omega will be cosine squared, right? And the other thing which is when sine and omega, cosine and omega, it will be sine times cosine. So what should I do? How can I evaluate this integral? Let's go back to the table that I showed you earlier here. Now, when look at property, let's see, we have cosine times cosine. Property number 4. Cosine times cosine, when n does not equal to m, it will be 0. While cosine times cosine, when n equal to m, this means cosine squared will be t over 2. How about sine times cosine? It will be 0. And number 5. And if it is, no matter if n equal m or n does not equal to m, everything will be 0. So based on property 4, 5, and 7, we can say, so here, from table 5.2, property number 4, when k, property number 4, and we will say like, I would say like the case. Case number 1, part A, when k equal n, this yields cosine squared and omega naught t. So using property number, what was the property number 7? It will be t over 2. Then for part B, when k does not equal to n, it will be using property. It will be cosine k omega t, cosine n omega t, and here n does not equal to m, or k does not equal to m. This yields, while I'm using property 4, 3, 0. Again, property 4, here it will be 0 if n does not equal to n. Then sine and cosine, this is the second term, it will be 0 no matter if k equal to n or not. You see term 2, it will be 0 no matter if k equal to n or not. So I would say like, case number 2, a and b, either k equal to n and k does not equal to n, both of them will be 0. Using property number, what was the property? Number 5. Okay? As a result, let's substitute them. So I said that here, when k equal to m, this will be t over 2, k does not equal to m 0, k equal to m, or k does not equal to m, both of them will be 0. So this term will be 0, this term will be only t over 2. So as a result, the integral from 0 to t, x of t, cosine, and omega naught t dt will equal to the a sub n times t over 2. That is the integral. So we need to calculate a sub n. A n will be 2 over t, the integral from 0 to t, x of t, cosine, and omega naught t, and property. Okay? Does this make sense? It's just like the evaluation of integrals. Step number 3, we need to calculate Vn. I can go through this. Step number 3, we need to calculate Vn. How to calculate Vn? We'll do the integral from 0 to t, x of t, sine, and omega naught t, dt. So it's going to be as, when we divide it, it will be 0 to t, a naught, sine, and omega naught t, dt, plus the sum of the integral from 0 to t, sum of k equal 1 up to infinity, a sub k, cosine k omega naught t, sine m omega naught t, dt, plus the integral from 0 to t, the integral or the sum from k equal 1 to infinity, b sub k sine k omega naught t times sine m omega naught t, dt. The integral of the sine over all k will be 0. Cosine times sine, the integral we said according to the property number 5, this will be 0. Then here we have two cases when n equal m, or actually when k equal n, or when k does not equal to n. When the k does not equal to n, this will be 0. This will be t over 2. So in summary, as a result, 0 over t, x of t, sine and omega naught t equals to bk times t over 2. As a result, bk will be, or actually let's say b equal 2 over t, the integral from 0 to t, x of t, sine and omega naught t. Then that's how we calculate B. Okay. Any question? So again, like these derivations, just for information to see how we can calculate the coefficients. So the overall analysis, Fourier series, any periodic signal can be presented into DC signal, which is constant value number, and combination of sine and cosine. When you add all of them together, this will be presenting a signal. It can be presenting sine, cosine, square wave, pulse train, etc. Then that's for the periodic, and we can say that the thing, which is in how to calculate the coefficient, which will take more complicated integrals. Now, there is an example here, or let's look at this table, which is, this is an example of non-periodic signals, and how can we represent them into Fourier series, like this. We have a square wave. You see the square wave is 4 times a over n pi, so here we use n instead of k, whatever. Sine n pi over 2, cosine n pi over 2. So you can see the square wave can be presented into an infinite number of product between sine and cosine. That's like even like this, the other part shifted, it's time shifted square wave. This is how can we present it. And there's a pulse train. You can see the triangular, etc. Let's just have a look at the pulse train. Let's explore it. Let's see how we can do it. So let's discuss the pulse train from table 5.4. We're going to take example pulse train Fourier series. So pulse train, according to that, x of t equal a tau over t. T is the period, tau is the magnitude, plus k equal 1 to infinity a over k pi sine k omega naught tau cosine k omega naught t. And look at the brackets plus k over k pi. Then times 1 minus cosine k omega naught tau k is times sine k omega naught t. Okay, that's the expression. Let me double check. Such that tau is actually the constant of 1,000 volts. Then let's do some comparison. Let's compare this with the original equation. The original equation is a naught plus the integral from k equal 1 to infinity ak cosine k omega naught t plus bk sine k omega naught t. Now, the question is, can you determine what's the corresponding values of a naught, a k, bk? Make a comparison. This is a naught, right? This is ak. This is bk. Correct? Is this correct? Just make a comparison. Then you can say again, a naught equal a tau over t, a sub k equal a over k pi, sine k omega naught tau, then b sub k equal a over k pi times 1 minus cosine k omega naught tau. Okay? Then here we can again demonstrate the pulse train using this infinite series. Okay, let's have an example. Assume pulse width equal to seconds, period equal 8 seconds, and also the magnitude pulse magnitude equals to 2. So with this situation, we need to determine by saying that the pulse width, which is a equal to period t equal 8, pulse magnitude, pulse width tau equal to period 8, then pulse magnitude, which is a equal to 2. Okay? Now, let's plot this function. We need to plot it. Plot using MATLAB. Here's the code. Here's the MATLAB code and how to plot this. Here, the first thing we need to do is define A. Define A, define tau, define t. Then, keep in mind, we need to determine something we call an ampere. Then we need to do like different cycles. So we define A naught. Then since it's infinite, it's a series, we will put a 4 from k equal n, then n4. Then we can calculate the coefficients A naught, AK, DK. After that, we can do the plots. This is related to the plot. how to assemble the plots. Then we can do during some plots. So you can like read this code to see how we do it, but keep in mind it's infinite series. So it's infinite series. Are we able to plot until infinity? No. So we need to do some coefficients. So we need to do calculation. Let's do, for example, here in this code, we did the number of coefficients until 10. So we started from k equal 1, 2, 3 until we stopped at 10. If you want to modify it, you can make it, for example, n equal 50. If you change n equal 50, you can make it k equal 1, 2, up to 50. So using this code, if you want to make it 100, you can make it 100. But you cannot make it infinite. And of course, the larger number, the longer processing time. It will take so long to process. Especially if you're putting, for example, 1 million. It will take a lot. You are inside a folder, it will keep doing this. While if you do it in like 10 times, you will do this. Maybe 100 times it will take more time, but less time. So sometimes related to the computation. So what's the best value to get a good width? That's the challenge. Should I put 10 as a roughly number? Or should I put, we have an infinity, but in real life, as an engineer, you cannot make infinity here, so we need to define the infinity as a very large number. This very large number can be 100, can be 1 million, can be 10 million, can be 10. So how can I judge on this? Let's assume we choose n equal 10. This is the waveform in a blue color, and while in the red color here, this is what the waveform should be. It's a train wave. It should be like a signal, like this wave. So we realize, we see some here, some ripples. It is not 100% signal, which is not pure enough, or not 100% square wave. So there's some problem, something we call it some unwanted thing, undesired things. Someone will call it some harmonics, which is something that we don't prefer. Imagine that you are sending this signal for a motor, and that motor will turn on and off. So if you see this will cause the motor ripple, it will vibrate, which will affect on it. Imagine that you are in the elevator, then the elevator sometimes bounce, so you don't want this to bounce a lot. So depending sometimes on the application, sometimes I don't need to have that much of accuracy because it's trivial. If it is for water pump, or whatever, if it is for where is a human being there, we need more comfort. We need more comfort, we need more accuracy. So whatever. Here, this is something undesired. And the other plots, here's when we plot A of k coefficient, here's B coefficient. So we see this coefficient. And most likely, the dominants are in the highest order. This is the lowest number of k's, which is k0, k1, k2, or I'm sorry, a0, a1, a2, b0, b1, b1, b2, b3, there is no b0, b1, b2, b3, etc. The lowest number will be dominants. That's why we see a trend for the square wave. While the missing of the other terms will cause these problems because there is some missing information. You can imagine this that when you take a photo, capture a photo using your cell phone, you can use 4K, 2K, HD or full HD, or you can use the SD. So when you look at the resolution, you will see the resolution for 4K is better than, for example, HD, right? Why? This one has more information. This one has bigger size, more information. While with, for example, HD or SD, they have lower information. So if you zoom it, you can notice the difference. When you zoom 4K and zoom SD, you'll notice some missing information, right? So basically, we can say 4K is better because you have more resolution. But sometimes when you have a small screen, I don't need to have 4K. Sometimes when you have a very small screen, you will not notice this is SD or this is HD, this is 4K, because you're not doing zoom, like maybe for a small screen, right? So sometimes I don't need to make over-complex. So it's enough to have. I don't need to buy more expensive or take more resolution, take more energy. Then the same thing here. If you increase the number of samples, you increase the resolution. So let's make 10, 20. Make it 20, the ripple are less. Here. Then the number of terms we can calculate it like this way, the coefficients. Let's make it 40. You see the ripples are getting less, which means now we are trying to get a better resolution image. Okay? A better resolution waveform. This is still not 100% square wave. There's some harmonies. But the question is, depending on my application, in my application, are we allowed to have this part, this accuracy? If not, let's increase. If we need more accuracy, okay. If, for example, we say that's fine, that's fine. Then it's a trade-off. Here, and 1,000. With 1,000, you see, it's almost square wave. Right? That's what we want, pulse trade. Look here. Look at this. We still have a little bit of problems. This will 100% disappear when you make an infinity. In real life, you cannot make an infinity. But what we will do, we will increase number of n until we will not notice this. This will be negligible. So we can say, for example, when in your standards, does your standard accepts 98%? Is correct? Do you accept 99%, 99.9%? We cannot reach 100, we can reach 100 at infinity. But you accept 99%. 98, 92, 80%, depending on what's your standard, what's your application. So we cannot say this is correct depending on what you want. Yes?
If you were like an average or like a Gaussian load over that spot, would it like smooth it out your application?
Actually, I'm not sure about it, but the thing here, which is, I would say, like, it's a trade-off problem. So do you need more accuracy, or do you need it with more accuracy? With higher computation of inputs, or less computation of less accuracy. Then, until reaching a point, they say, okay, this accuracy is, we need to like pay more for the comfort, or say, okay, I'm fine with this. We need to do more. Okay, so that's one example of using the pulse tree. Now let's go to another example, sawtooth signal. Go to the table. Sawtooth is it here? It's here, which is the superficial position. Now, let's assume we have another part of sawtooth, because this sawtooth starts from negative A to A. How about if I have a sawtooth differently? So what should I do? There is, for example, you have a backbone sawtooth, there's a different part. Well, let's assume this signal. Here's this of T, and it starts like this. So use a period T, 2T, 3T, and all of the magnetic A. And of course it's continuous forever, it's periodic, continuous forever. Now, we need to find Fourier series for this. So according to our analysis, to find Fourier series, it is, let me write the overall formula for Fourier series, x of t equals to a naught plus the sum from k equal 1 up to infinity, a sub k cosine k omega naught t plus b sub k sine k omega naught t. Right? That's the general form. Now, what do we know about omega naught and the frequency? So, omega naught equals 2 pi times f. Here, omega naught equals 2 pi times f. or in other words 2 pi over t, because 2 pi times f equal 1 over t. Okay, does this make sense? So we can say x of t, substitute this here, a naught plus sum k equal 1 up to infinity, a sub k cosine k omega naught, which is 2 pi, so 2 pi times k t divided by t uppercase plus b sub k sine 2 pi k over t uppercase t. That's it. Now I wrote the jiggle for it. There is 3 unknowns: a naught, a k, e. So we need to calculate these 3 unknowns. So we have 3 unknowns, which is a naught, a k, e. Let's calculate the first one, which is the a naught. A naught is actually 1 over t, the integral from 0 to t, x of t dt. And again, it is the average value. Now, what is x of t? Let's look at for a period of time, which is this period. Or this period. You will realize it is like a ramp shape, right? It's like a ramp shape. So basically, we can say to find the equation, it is the slope. Slope here is a minus 0 over t minus 0, so it will be a over t. Therefore, we can say x of t equals to a over t times t. Okay? This is only during one period. During one period. So we can substitute this here. It will be 1 over t, the integral from 0 to t, a over t, t dt. So it will be a over t squared, the integral from 0 to t, t dt. What's the integral of t? It will be a over t squared substitute from 0 to t, which is going to be as before the 1 half. T squared to 2, a over t squared times t squared over 2 minus 0 over 2. Then we will see that 0 this will go, t squared will go. So the answer will be a over 2. So as a result, a naught will be a over 2. So the first unknown done. Okay? The next thing is to calculate b. Also to calculate a of k, the second unknown. A sub k, according to the equation, 2 over t from 0 to t, x of t cosine k omega naught t dt. And we know x of t is a over t uppercase times t on lowercase. So let's substitute it, which is 2 over t, the integral from 0 to t, a over t, t cosine k omega naught t. So a over t is a constant, we can move it to the other outside of the integral, so 2 times a over t squared, the integral from 0 to t, t cosine k omega naught t dt. Now, how to find t cosine k omega naught t? It's not easy. Remember calculus 2, integration by parts? Okay, you need to go back and recall. So I'm just going to write this for the numerator, so integration by parts. This will be your homework, review it. It is something like, you say u equal t, then du equal dt. So we'll assume this as u, this is as dt. Then dv equal cosine k k omega naught t dt. Therefore, v will be the integral of it, which will be 1 over k omega naught sine k omega naught t. Then, using integration by part with the product minus integral. So in other words, integration by parts, the integral of u dv equal u times v minus the integral of v. This yields the integration by parts will be this equation a sub k will be 2 over a over 2 squared the integral of uv substitute from 0 to 2 minus from 0 to 2 v du, and I'm just going to write the form substitute these numbers. Then we will continue later of substituting u, which is 15 by 0, which is t, times v, which is 1 over k sine k omega naught t, all of it substituted with 0 to t, minus integral of v, 1 over k omega naught, and from 0 to t, sine k omega naught t, du, which is... Okay, so we will continue in this later, but this lecture, but please make sure to review the field of parts.